Hello everybody and welcome to the Unit 8A.5 video number 1. The goals of this particular video are to find all the zeros of a polynomial, and so we're going to be focusing on polynomials of degree higher than 2, be able to find all rational zeros of a polynomial using something called the rational zero test, and then also again to be able to show that a root is or is not a factor of a polynomial. And from earlier videos, this means that it has a remainder of 0. So some vocab review before we start. As you know, based on Unit 7 and so far in this unit, zeros have other names, roots, x-intercepts, and solutions. And a lot of the time when we wanted to find a root, an x-intercept, or a solution, we wanted to have a quadratic. So I'm going to write a note here that we want a quadratic in order to solve. So my goal for this video is, if you're given a polynomial of higher degree than 2, is to eventually use synthetic division to get it to a quadratic so that we can factor or solve how we have before. Another review topic that we'll be discussing in just a minute is, again, what a rational number is. And a rational number is any number that can be written as a ratio or a fraction. We're going to be going over specific examples of that in just a minute. But first, I would like to solve this example that comes next in your notes. Find all the zeros of f of x equals x cubed minus 3x squared plus 9x plus 27. Now, before I mentioned that eventually we're going to be using synthetic division in this video, but we don't actually need to on this first example because some of you might notice that this could factor by grouping. So what I'd like you to do is pause the video, start factoring this by grouping, see if it works, and try to find the zeros yourself. So please pause now. So when I solved this, I took out a GCF of x squared in the first two terms and a 9 in the second two terms. When I took out those GCFs, I got it to factor to x plus 3 and x squared plus 9. When I solved, I got one real root of negative 3, 0, and I got two imaginary roots of positive and negative 3i. So if I were graphing this, which we will be in a little bit, the only root that I'd be able to see on the coordinate plane is negative 3, 0. Please feel free to pause this if you want to write down the work, or rewatch this if you need to. But what I'm going to do is continue on to the next slide, and I'd like to review for you what rational numbers are, what some examples are, as well as irrational numbers. So example of rational numbers, remember from earlier, is any number that could really be written or turned into a ratio or a fraction. So some examples would be the number 2/3 is initially a fraction, so it has to be rational. If I had the decimal 0.20, that could really be written as 20 over 100 because of the two placeholders, which would reduce to 2/10 or 1/5. So this decimal can be changed to a fraction, so it's rational. As long as my decimal has a particular pattern, like if I had 10.3 repeating, this is really 10.33333 forever, which is really 10 and 1/3, so that's also rational. And what I mean by patterns, and I'm checking a few with my calculator right now, if I had 0.17171717 on and on, if I press math enter in my calculator, this can convert to 17/99, so this has to be rational. And even if I had a pattern like 0.123 on and on and on, the same pattern, if I check in my calculator, that also can be changed to a ratio 41 over 333. However, an irrational number is a number that the decimal never repeats and never ends. Never repeats and never ends. So there's no pattern to be seen. Some examples of this would be the square root of 2. So that is 1.4142135562 on and on and on. No pattern here. The square root of 3 is also an example, 1.732050808. I'm getting these from my calculator, by the way. I wish I had these memorized. That would be very impressive. I am not that impressive, unfortunately. Pi, 3.141592654, on and on and on. Even a decimal like 0.1102, 03, 04, 05, on and on, this doesn't repeat and doesn't end, so that would also be considered an irrational number. Now, after that review, we're on to the main part of our lesson, which is about the rational zeros test, which helps us solve if we cannot initially factor, and it also helps us get to a quadratic. So that eventually we can factor. So whenever you hear the rational zero test, before I explain what it is, the goal is to use it when we cannot initially factor and when we would like to get a quadratic so that we can continue to factor. And what the theorem says is, first, we would like to find all possible rational zeros. Now, before I read what the theorem is, let me point something out to you. If I asked you to factor 2x squared minus 5x plus 10, I just made that up. What I'd like to focus on is the a and the c term. If you were to factor by guess and check, what you think about is what two numbers multiply to be 2, and that would just be 1 times 2, and what numbers multiply to be 10. Well, that's either 1 and 10 or 2 and 5. So finding these numbers here is somewhat what the rational zero test is asking us to do. So if I read the rational zero test now, if p of x is a polynomial with integer coefficients, like this example down here that I'll box in green, and if p divided by q is a zero or a root of the polynomial, then p is a factor of the constant term, so this represents p here, the 12, and q is a factor of the leading coefficient, so the 5 would represent the q. So it says that p divided by q would be a 0. So if I would like to find all the possible zeros or all the possible x-intercepts of this polynomial, what I would have to do is divide all of the factors of p by all the factors of q. In this case, because it could be positive or negative, we would have plus or minus all the p's over plus or minus all the factors of q. Now this so far is not so helpful, so let me show you what that means in terms of this example. The numbers that can multiply and be 12 would be 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. 1, 2, 3, 4, 6, and 12 are all factors of the constant term p. The only factors of q are 1 and 5, so plus or minus 1 or plus or minus 5. The reason we have to include plus or minus is, as you know, 12 could be a negative times a negative, so we have to include everything possible. Now, what this really means is we have quite a few possible solutions here. And the reason that this matters I'll get to in just a minute, but if I want to continue this, here are all my possible answers. I have to take everything on the top and divide it by 1 on the bottom, and then divide everything by the top by 5. So my possibilities would either be plus or minus 1 if I divide these, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus and minus 12 if I divide everything by 1. Then I also have plus or minus 1/5 as an option, plus or minus 2/5 because I'm doing this divided by this, plus or minus 3/5, plus or minus 4/5, plus or minus 6/5, and finally plus or minus 12/5. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 possible zeros or roots. Now, that might seem overwhelming, and the question you might be asking yourself, understandably so, is why in the world do I care about this? Well, it helps us narrow down the number of roots without a calculator. And even if we do have a calculator, it helps us use the graph to our advantage. And I'll be going through what that really means on this example. If I look at what I want next, I want to find the zeros of the polynomial that's the exact same that we just found all the possibilities. So here are all my possible rational roots. Rational meaning can be written as a fraction. So what I did already was I graphed the polynomial. So this is it. And it looks like it crosses the x-axis 4 times. And I notice that -1 is a rational answer and 1.2 is a rational answer, both of which we got originally as options. 6/5 is really 1.2, and we did get -1 as an option. So I can pick one of these to start with because it was part of my list, and I can see that on my calculator it does actually exist here and here. So that's what I mean by using the graph to your advantage. So if I went back to the problem, if I want to find all the zeros, I know that x equals -1 is a 0 based on the graph, and x equals 6/5 is a 0. Let's say I start with -1 because it's a little easier to work with. If I use synthetic division and I write -1 and then the lead coefficients of 5, -1, -16, 2, and 12. Remember that synthetic division reduces your degree by 1. So if I start the synthetic and bring down the 5, I multiply diagonally and get -5, combine down. -1 times -6 is 6, combine down. -1 times -10 is 10, combine down. -1 times +12 is -12, and if I combine down, I get a remainder of 0, which means that my polynomials now become 5x cubed minus 6x squared minus 10x plus 12. Now, because I want to get this to a quadratic so I can continue to factor, what if we did the rational root test again? And I know that another root that works is 6/5. So what if I took 6/5 and I did synthetic division with this one? So I can do it more than once. Write my lead coefficients and go through the process. Bring down the 5, multiply 6/5 times 5 over 1 and get 6. Combine down, 0 times this is 0. Combine down, get -10. -10 times 6/5. 5 goes into 10 twice, so that's -12. And again, I combine to be 0. So I have another remainder of another remainder of 0, which means this polynomial ends up being a degree lower than the previous. So because this was a cubic, this is now 5x squared plus 0x minus 10. And because it's a quadratic, I can set it equal to 0 to keep solving. So that would really be 5x squared minus 10 equals 0, which would be 5x squared equals 10. I'm not going to factor, I'm going to use square roots. So I'm going to divide the 5 out and get x squared equals 2, which means that my other possible answers are plus or minus root 2. The reason root 2 was not in my original list here was because that's not rational. Because remember, root 2 is an irrational number. So it looks like I do have 4 roots, 2 rational, 2 irrational. So we'd have -1, 0, 6/5, 0, positive root 2, 0, and negative root 2, 0. So these are all my rational roots. Doesn't look like we have any imaginary this time. So here's where I'm going to pause this first video. I want to start the next example on video number 2. So if you could join me there, that would be wonderful. Thanks, everyone.